Ionic compounds are very, very common. They're present in the Earth's crust as minerals. They're present in the foods that we eat. Here are a couple of examples. Medicine, antacids, those are ionic compounds. Morton salt. Light salt is a mixture of sodium chloride and potassium chloride. That's how it's lower in sodium. And here's a couple of examples of minerals. These are ionic compounds that are found in the Earth. Now, here we have an example of an ionic compound where there's two different, you could think of this as two different cations. And so I'm not going to try to mess with you about that one. Ionic compounds are very stable because those ionic bonds are very, very strong. And so the compound stays together. Ionic compounds tend to be solids at room temperature because they hold together very well. So we need to learn how to write formulas for ionic compounds and how to name them. Now, this naming business and the dealing with the ions is going to come up over and over again through the semester. So please ask me questions today if you're not understanding so that we can just clear it up right away, okay? So when we're writing formulas for ionic compounds, the first thing we do is we write the element symbol for the metal, that's the cation, and we're going to put the charge on it. These are notes to ourselves. So we're going to write the formula for the metal cation with its charge, and then we're going to write the symbol for the nonmetal with its charge. We're going to look at the charges to see how many of each ion that we need, how many cations, how many anions, because in a compound there is no overall charge, it's neutral. So the total positive and negative charges have to add up to 0. Sometimes that's really simple and sometimes it's not quite so simple. So we're going to put subscripts on the cation and the anion as needed to represent the correct ratio of ions, and then it's always a good idea to check your work at the end. So ionic compounds always contain positive and negative ions. The first element is usually a metal. The one exception you need to know about is the ammonium ion. That is a polyatomic cation that we will see in ionic compounds. So you need to know that one. So the sum of the charges, positive and negative, add up to 0. That means we have an equal number of positive and negative charges. And the formula for an ionic compound is the smallest whole number ratio of ions. That is almost always, like 99%, it's the empirical formula is the lowest ratio. So let's practice this. Let's write the formula for the ionic compound that forms between potassium and sulfur. So potassium is a metal, and its element symbol is K. Sulfur is a nonmetal, its element symbol is S. We need the charges on these ions, and these come from the periodic table. Potassium is in group 1, so it has a +1 charge. So I indicate that it has a +1 charge by putting a plus sign as the superscript here. Sulfur is a nonmetal, it's got a negative charge. So we look at sulfur on the periodic table and we count from the noble gases. So argon would have a charge of 0, and then we go to the left, chlorine's -1, sulfur's -2. And so we write 2- up here. So now we have the formulas for each ion with their charges. Charges are important because that tells us how to put them together. So this has a +1 charge, that has a -2 charge. So if we have one of each of these, their charges will not add to 0, right? So what we need is another potassium ion. If we had 2 potassium ions, then our total positive charge is +2. With one of these, -2, they'll add up to 0. So the formula for this compound is K2S. You don't write the charge in the formula for the compound. And you might ask, well, why? That would make the formulas really, really messy. So what I have observed as just sort of a general principle is that we are trying to be as concise as possible. We're not including a lot of extra information. We're just putting down the minimum needed to be specific about what we're talking about. So K2S. Let's look at aluminum and nitrogen. So the symbol for aluminum is Al. And I tend to write my lowercase l's in cursive so that they don't look like ones or capital I's. So for me, this is a 1. This is capital I. So I put the serifs on top and bottom. That's the capital I. And this is a lowercase l. Some students like to write in all caps, and they make their lowercase letters just small capital letters. You can do that anywhere except element symbols. Okay? So there's aluminum. What's the charge on an aluminum ion? 3+, because it's in group 3A. It's a main group element. So it's 3+. Nitrogen has a symbol N. What's the charge on a nitrogen ion? 3-. So we can look at these charges. They are opposite but equal. +3, -3. So we just need one of each of these. So I think of just shoving those two guys together. And we have A, L, N. I don't write the ones because if it was 0, I wouldn't write the symbol at all. And if it was other than 1, I'd put a number there. Any questions? Let's talk about names. Some compounds have common names, and they may have multiple common names. But we've developed systematic names so that every compound has one ultimate name. Okay? Every compound has one unique descriptive name. It's a systematic name. And there's pages and pages of rules about how you figure those out. We're going to keep to the simpler ones, and so it won't be that bad. There are different systems of naming for different types of compounds, not unlike the different systems of naming that people have for their children. So in the United States, typically the child takes the last name of the father, right? And it'll have a first name and a middle name that are just chosen at random by the parents. In other countries, like in Sweden, years and years ago, the son would take the father's first name as his last name with son at the end. So my maiden name was Johnson. So if I was in that older period of time, that would mean that my father's name was John. And so my last name would be Johnson, which would be different than his last name, which might have been Anderson, because his dad was Anders, right? Kind of confusing. And then for the girls, actually my name wouldn't be Johnson, it would be Johnsdotter. They use Dotter for the girls, right? So it's a different system of naming. There are multiple different cultures that have different ways of naming their children, right? And if you understand the culture, you understand the system. So here, we have to think about these compounds as belonging to different cultures, and we need to understand the culture that this compound is in so that we can name it correctly. So identifying what type of compound it is the first step in naming. And we've already learned how to do that, to distinguish between ionic compounds and molecular compounds. So ionic compounds are usually composed of metals and nonmetals. So here are some examples. The first element in all of these is a metal. Now there's one exception that you need to remember. If it starts with NH4, it's also ionic. So naming ionic compounds falls into two categories. And sometimes the books will talk about type 1 ionic compounds and type 2, and I think that's a little silly. What it comes down to is some metals only form a single kind of ion. They always have the same charge. And others are not as predictable, and they can form 2 or 3 or more different ions. When you have a metal like iron that can form a positive 2 or a positive 3 ion, just calling it an iron ion isn't good enough. Potassium, we know, is always +1. That's simple. But iron, we need a little more information because it can form more than one type of ion. So these are the metals that form one cation, one type of cation. The group 1A metals, group 2A. Now, beryllium's not colored in here, but that's okay. You don't even need to remember that. He's just being squirrely. So if it's in group 2A, it's got a positive 2 charge. Over here, group 3A, aluminum. We're not going to really run into the rest of these. Aluminum's the one you need to remember. So there's aluminum, and then there's 2 more, zinc and silver. So those are the ones I want you to remember. Group 1A, 2A, 3A, zinc, and silver. Now scandium is also over here. Scandium only forms a +3 ion. I don't expect you to remember that one. Scandium's very rare. We're just not going to run into it much, but it's there. And depending on who you talk to, nickel also only forms 1 ion, but we're going to go with what your book says. So group 1A, 2A, 3A, zinc or silver. I'll be repeating that over and over and over again. Those are the ones that always form the same charge. We know what the charge is from the position on the periodic table. I'm like, well, I don't know about zinc and silver. Here's how you remember zinc and silver. Aluminum is in group 3A, is +3. And then I think of going down the stairs, right? Doesn't that look a little bit, a little bit like steps, right? So I'm going down the stairs. 3, 2, 1. This is +3, this is +2, that's +1, okay? That's how I remember it. Then there's the others. So if it's not in groups 1A, 2A, 3A, zinc, or silver, it's in the other group. It can form more than 1 ion. And so then when we give the name of the ion, we have to specify which one. So it's a little bit like the kings of England, right? King Edward. Well, which King Edward? King Edward II, King Edward III? There was a whole string of them, right? They used Roman numerals to keep track of them. So in chemistry, we also use Roman numerals. So chromium can form 2 different ions, and you're not going to be able to predict this from the periodic table. It can form a +2 or a +3 ion. So this is called chromium 2. My pointer's, there we go. Chromium 2, because it's +2 charge. Chromium 3 has a +3 charge. We don't use a Roman numeral for something that doesn't need it. You know, my son, Thomas Kawagoa, he doesn't go around calling himself Thomas Kawagoa the First, right? Because we don't need to specify that. There's only one of him. Now, if there was a son, Thomas Kawagoa II, right? But we don't add the numerals unless they're needed. So groups 1A, 2A, 3A, zinc, and silver, no Roman numerals. Any other metal, we put a Roman numeral in parentheses that indicates the charge. And a quick review of Roman numerals. So we should be able to count up to about 6 or 7. So these are Arabic numbers. I ran out of space. 1, 2, 3, 4, 5, 6. So Roman numerals. For a 1, it's a capital I. For a 2, it's 2 capital I's. A 3 is 3 capital I's. Mastering chemistry cares whether you punch in 1 capital I or lowercase l. It'll look the same on the screen, and it'll drive you bananas because you're like, I did it right and it's saying it's wrong. You have to do the capital I, okay? It can tell the difference. So 3 is 3 capital I's. You might think, well, this is just tally marks. Well, that was going to get unwieldy, so let's skip ahead to 5. 5 is capital V. Don't ask me why. The ancient Romans decided on this. So 5 is V, 4 is 1 before 5, right? So the Roman numeral 4 is a 1 before a 5. And a Roman numeral 6 is 1 after. So V with an I after. And 7 is a V with 2 I's after. And 8 is a V with 3 I's after. And now it's getting a lot of I's, and so then 9 is 1 before 10, which is X. 6 is probably good enough to know. Here we've got tin 4 and lead 4, okay? And you do need to use the Roman numerals. Those are the charges on the ions. Here is a system that is still sometimes shows up, but you don't need to memorize it. So it used to be that these 2 ions were distinguished as with suffixes, so chromous and chromic ion. There, it was, it's there. It's confusing. It doesn't tell you the number, okay? Just be aware. So this is a summary of my tricks for these things. So group 1A, group 2A, charge equals the group number. Group 3A, we've got the charge equals the group number. And then there's this triangle. So 3, 2, 1. Silver's always +1, zinc's always +2. The book doesn't mention it, but cadmium is also just +2. So these guys don't use Roman numerals. So groups 1A, 2A, 3A, zinc and silver don't use a Roman numeral. For anything else, use the Roman numeral. I won't try to trick you with scandium or indium or any of those weirdos. Okay? So those are cations. Anions. We have monoatomic anions with the single atom, and we have the polyatomic ones. So a monoatomic anion would be a nonmetal, and we can predict its charge from the periodic table. So we've already learned about that. We need to know how to name this. What we do is we take the ending of the element's name and we change it to "ide." So fluorine becomes fluoride. Chlorine becomes chloride. I think of metals as being masculine, like men, and then nonmetals are non-masculine, so that would be the women. And we're going real traditional here. But when a woman gets married, traditionally, she changes the end of her name, right? She changes her last name to match that of her husband. So here, these nonmetals, which I think of as feminine elements, they change the ending of their name when they become part of a compound, which is a little bit like getting married. You're hooking up with somebody, right? Okay? So those are the element names. Charges, most people like just count backward from the noble gases. Or you can do group number -1. So, naming binary ionic compounds. Binary means 2. So this is just 2 different elements. It's going to be a cation and a monoatomic anion. So to name this, you name the cation, and then you name the anion. The anion is the element name with the ending changed to "ide." Like human names, there's a space between the first name and the last name, but these are not proper nouns, so we do not capitalize them. The name of the cation always goes first. It's always the metal and the non-metal, just like on a formal invitation, it's always Mr. and Mrs., right? It's never Mrs. and Mr. It's just a convention, okay? Metal first. So if we look at this compound KCl, there are 2 ions. There's the potassium and there's the chlorine. So we name the potassium ion first. Potassium is group 1. It doesn't need a Roman numeral. It's just potassium. Chlorine is the nonmetal. She has to change the end of her name, so chlorine becomes chloride, and the name is potassium chloride. Okay? CaO, 2 ions, 2 elements, calcium and oxygen. Calcium's in group 2, doesn't need a Roman numeral, it's just calcium. Oxygen changes the ending of the name to -ide calcium oxide. Any questions? Okay, let's name this compound Ag3N. So there are going to be 2 ions. So there's going to be Ag and there's going to be N. What is the element name for Ag? Silver. Is it in groups 1A, 2A, 3A, zinc, or silver? Yeah, it's silver in the group 1A, 2A, 3A, zinc, or silver. No Roman numeral, just silver. And then N, nitrogen, becomes what? Nitride. So nitrogen becomes nitride. And that's the name. I don't do anything with that 3. I don't need to. We just name the cation, we name the anion. When we're going the other way, like we'll do here, where we have a name and we write the formula, this 3 we would get by looking at the charges on these. We don't have to do that when we look at the names, unless it's not in group 1A, 2A, 3A, zinc, or silver. So any questions on naming that one? Write the formula for rubidium sulfide. So this is the same process as write the formula for the compound formed between rubidium and sulfur. We write the 2 symbols for these ions. We look at the charges to figure out how to put them together. So the symbol for rubidium is Rb, and we find it on the periodic table. And it's over there in group 1, right? It's in group 1, it has a charge of +1. Sulfide is the ion of sulfur. We count backwards from the noble gases and we get -2. 2 minus charge. Those are the ions. We need to figure out how to put them together, and the charges are going to help us with that. When we put these together, the charges have to add up to 0. If we just have one of each, that's not going to work. If we put in another rubidium ion, now I'm going to have a total of +2 there and -2 over here. So writing that formula would be Rb with 2 as the subscript, S. Because I have 2 rubidiums and 1 sulfur. Any questions? So naming binary ionic compounds with the other kinds of cations. So if it's not in group 1A, 2A, 3A, zinc, or silver, we need to put the Roman numeral in parentheses. It goes after the name of the cation and before the name of the anion. So in a man's name, King Henry VIII, right? The 8th part goes after his name. When we have a name and we're figuring out the formula, the Roman numeral gives us the charge. If we're going from a formula to a name, we have to figure out, based on the relative numbers of ions and the charge on the anion, what that charge on the cation is. Let's do an example. Let's name CrBr3. It might be nice to name him Steve, but he's got a given name. So Cr and Br. So the first one is the metal. Cr is for chromium. Chromium has an H in it. So chromium, and then you ask yourself, Is chromium in group 1A2A3A zinc or silver? No. That means it needs a Roman numeral. So I'm going to put the parentheses here. I don't know what the Roman numeral is yet. I'm just going to save a space for it. And then I'm going to go on to the other element, bromine. And I changed the ending of bromine's name to "ide," bromide. So I have chromium blank bromide. There's a space between the parentheses and the next name here. There's no space here. So how do I figure out what the charge is? So I go look at the periodic table and you're like, oh yeah, it's not in group 1A2A3A zinc or silver. It's not going to help me. So what I'm going to do is I'm going to look at the other ion. So bromide has what charge? -1, right? And the formula tells me I have 3 of those ions, right? And the formula tells me I have 1 chromium ion. And I don't know what the charge is. It's plus something. Well, what's my total negative charge here from 3 bromide ions? It's -3. This is an ionic compound. It's neutral. So if I have a total of -3, then I must have also a total of +3, right? So it adds up to 0. So this +3, sometimes there might be more than 1 here. There might be 2 chromiums or 3 chromiums in the formula. That would be indicated by the subscript. Here there's only 1. So this +3 charge has to all be on that chromium. So this must be chromium 3+. I inferred the charge on the chromium from the formula and the charge on the anion. I had to figure it out. Chromium 3+, so that means that this Roman numeral is 3. The Roman numeral is the charge. It is not how many of that ion. There's only 1 chromium in this compound, in this formula. It's chromium 3 because the charge on the ion is 3+. Any questions? Some more practice. Name the compound FeS. We got 2 ions, a cation and an anion. There's only 2 elements there, so we've got Fe and we've got S. What's the name for Fe? Iron. Is it in group 1A2A3A zinc or silver? No, it isn't. That means it needs a Roman numeral. So I'm going to leave space there. Sulfur becomes sulfide. So I've got the name except for the Roman numeral. Now I look at the charges. What's the charge on a sulfide ion? 2-. This formula tells me there is 1 of each, 1 iron and 1 sulfur. So then the iron must be +2, right? Because the charges have to add up to 0. So then this is iron 2 sulfide. Any questions? Once you see the pattern, once it becomes clear, it's actually very simple. And you're all capable of seeing it, but some of you might need to ask a lot of questions and struggle a lot with it until it clicks. It's worth the effort, okay? Yeah?
Do you always write it with the parentheses?
Yes, you always put parentheses around the Roman numeral. Yep. So here's going the other way. Write the formula for ruthenium-4 oxide. So I'm going to write the 2 ions with their charges. Now, once you get good at this, you don't necessarily have to do this little scribbling stuff on the side. But until then, you really do need to write this out. So ruthenium is Ru, and the Roman numeral 4 tells me that this has a 4+ charge. Oxide is oxygen, And oxygen has what charge? -2. So how do I put +4 and -2 together? I need 2 of the oxygens, right? So if I add another oxygen in there, I've got a total of -4 over here and a total of +4 over there. So I need 2 oxygens. So this is going to be RB, nope, RuO2. Any questions? Are you familiar with the crisscross method? Probably have heard of this. So I'll show you the crisscross method on this one. You have to be careful with the crisscross. So when you look at the charges, if they are not the same, you can do crisscross. Up here, we've got +2, -2. Don't do crisscross, just stick them together. +4, -2, they're not the same. So we could crisscross, right? What that means is I'm going to take the 4 and make it the subscript over here. I'm going to take the 2 and make it the subscript over there. That would predict Ru2O4, which is not quite right. You have to look at, is this the lowest ratio? This is 2 to 4. I can simplify that. I can get to a lower ratio, RuO2. So the crisscross method can be helpful, but it can also point you in the wrong direction occasionally. And I think it's better to think about just, even draw them in. How many of each do I need so they add up? Any questions? What about those polyatomic ions? So polyatomic ions just have names. And their names are related to their formulas, but there's not a real direct relationship like there is with iron 2, right? So you just have to memorize them, and that's why I gave you a list of them at the beginning of the semester when things were a little less crazy. They're starting to pick up now in the 3rd week, so that you just memorize them. So if we're looking at the compound NaNO2, we're going to split this into 2 ions. Sometimes students get a little too creative and they're going with sodium and nitrogen and oxygen. You will only be asked to name things in this class that only have 2 ions. So 2 ions. The first one is going to be the metal. So sodium's the metal, and I can draw a line either actually or mentally and say, well, sodium's 1 and everything else is the other ion. So Na is +1 because it's in group 1. That's sodium. It doesn't need a Roman numeral because it's in group 1. NO2, if I've forgotten the charge on that ion, I could figure it out based on the number of each. There's one of these and one of those, so it must be -1. But I need to have memorized the name for that. NO2 minus is nitrite because you memorize it. And so to name the compound, we name the cation, and then we name the anion, and this is sodium nitrate. Any questions? The trickiest part there is memorizing those stupid polyatomic ions. Some common polyatomic ions. Some of these are more important than others. I'd like you to notice that ammonium is the only positive one here, so watch out for him. Some of these have a name that has 2 words, hydrogen carbonate. So HCO3 with a -1 charge, this is related to CO3 2-. The difference is this one has a hydrogen on it. It's a hydrogen ion, an H+, and so when I add H+ to this, it changes the charge, it decreases it by 1. So HCO3 is called hydrogen carbonate. Another name for it is bicarbonate. So I want you to be aware of bicarbonate. I won't use it on exams. I prefer hydrogen carbonate. That's bicarbonate, just gets confusing. Over here we've got, where is it? Here. So here's phosphate, PO4 3-. Hydrogen phosphate has one hydrogen ion on it, so then the charge is 2-. Dihydrogen phosphate, di means two, it has two hydrogens. Most of these end in either ATE or ITE, and most of these have oxygen in them. A couple of weird ones are cyanide and peroxide. Hydroxide, where'd you go? Here's hydroxide, OH-. That one's very, very common. You just have to memorize them. There are some patterns, and there are some ions that I will expect you to give me the name of or formula of, even though they weren't on the list to memorize. And we figure those out by following a pattern. So the polyatomic ions that have oxygen in them are called Oxyanions. They have oxygen and another element. And there are families or series of these. So there are two oxyanions with nitrogen. One has 3 oxygens, one has 2. So this one is nitrate and this one is nitrite. Similar for sulfur. There's sulfate and sulfite. The ite one has 1 less oxygen. It's like the light version. 1 less oxygen. Thank goodness the charges are the same. Okay? So my approach is I memorize the one that ends in 8. And I remember that the ite is 1 less oxygen, and so I'm good. Some of them have a series of more than 2. So chlorine is an example here. So here is chlorate. Chlorate is ClO3- because you memorize it. Here's the light version, chlorite. 1 less oxygen, so it's ClO2-. Like Bud Light has 1/3 fewer calories than regular Budweiser, right? Chlorite is the light version of chlorate. It has 1/3 fewer oxygens. What if we lose 1 more oxygen? Now we put a prefix that means below. Hypo means below. Hypodermic needles go below your dermis, your skin. Hypochlorite is 1 less. If we take chlorite and we put another oxygen on it, then it becomes perchlorate. Per means more. Think of hyper, right? Hyperactive, more active. So this is more oxygens. So these are the 4 oxyanions in the chlorine series. Chlorine and bromine are in the same family in the periodic table. They're both halogens. I think of them as sisters. They behave in similar ways. They have similar properties. So bromine and chlorine form the same types of ions. All that's different between bromate and chlorate is this one has bromine, that one has chlorine. Number of oxygens and the charge is the same. What do you think the formula for iodate would be? Iodine is also a sister of bromine and chlorine. So it would be IO3-. It's like they're sharing a sweater, right? The sweater fits on any of them. You just change the beginning of the name. Okay, so here's another slide of tricks. You memorize the 8s, you memorize the pattern, and here are the hints for the pattern. So you memorize that one. This is the light version. Hypo means below, per means more. And I have written this upside down of how they show it in the text. The names are the same. It's just, I think I like to put more on top and less underneath, because hypo means below. It should be at the bottom. Only the number of oxygen atoms changes. The charges stay the same. Okay? Naming ionic compounds with polyatomic ions. Okay, so SnClO3, 2. I haven't talked about those parentheses there. So ClO3 you should recognize as a polyatomic ion. That's chlorate. There are parentheses around it because it's like a bundle pack at Costco. You can't buy one bottle of ketchup. It's 2 bottles of ketchup and they're shrink wrapped together, and that's really tough shrink wrap that you can't break, right? To go home and get out a scissors. ClO3 is a chlorine and 3 oxygens, and they come as a package deal. So ClO3 is the ion, and then parentheses are like the shrink wrap, and on the outside that tells us how many of those packages do we have. We use parentheses around polyatomic ions when there's more than one. If there was only one, we wouldn't use the parentheses. If it's a single ion, a monatomic ion like chloride, then we're not going to use the parentheses either, even if we have 5 or 6 of them. The reason we need parentheses here is because it gets confusing. I just messed up my iPad. If I wrote this formula without the parentheses, what does that look like? 32 oxygens and 1 chlorine, right? That's going to be confusing. So the parentheses are put in there to avoid confusion. Okay, so enough of that. We need to name this. 2 ions. So there's the metal, and then there's everything else. Everything else is a single ion. There's 2 of them, but it's just one kind of ion. So Sn is which element? Tin. Is tin in groups 1A, 2A, 3A zinc or silver? No. It needs a Roman numeral. We don't know what it is yet. Put parentheses, fill it in later. ClO3, what is the name of that? Chlorate. Why? Because you memorize it. It just is. That's what they decided to call it. Well, I wrote chlorate, but it crashed on me. Okay. So tin blank chlorate. Now we need to look at what we've got going on here. So ClO3, 2. That means I have 2 of these chlorate ions. What's the charge on a chlorate ion? -1. Because you memorize it. So then I have a total of -2 charge, right? That means I must have a total of +2 charge because this is a neutral compound. The +2 charge is shared. Well, it doesn't have to be shared. There's only 1 tin. So that must have a +2 charge. So I write the Roman numeral 2 in here. Tin 2 chlorate. Any questions? We have to be very precise here. It's like an email address. You get 1 letter wrong, it doesn't go, right? Did that the other day. Looking up something I needed to send to someone, and on the website, her name was spelled wrong. Supposed to have 2 L's and I only had 1. So I followed the pattern of the email addresses here at Fresno City and sent it off, and it came back. What the heck? Yeah, well, I spelled her name wrong because they spelled it wrong on the website. It's got to be exactly right. If I change this letter A to an I, it's a different compound. If I change this number 2 to a 3 or a 4, it's a different compound. Okay? Details matter. Let's do the opposite. Write the formula for cobalt-2 phosphate. Yeah, question in the back.
So on the test, if you misspell like just 1 letter, would that be like taking on partial or?
That's a good question. So if you spelled it wrong or you made one of those little mistakes on an exam, would that be partial credit? Would be the whole thing wrong? The exams will mostly be multiple choice. And so a question like this would definitely be a multiple choice question. And so there could be distractors like this. There might be one that says tin 4 chlorate. There might be another one that says tin 2 chlorite. So like if you're forgetting the H on the chlorine part, that's not going to show up as a distractor, but the 8, the ite, the number, or, you know, I might say, well, what might they think that SN is other than tin? And I might stick that one in there, you know, sanium or something, right, that you might get fooled by. So if you choose the wrong answer there, then yeah, you lose all the points. But you do have 4, possibly 5 to choose from, so that limits down the number of mistakes you could make. Okay, cobalt 2 phosphate. We need to write the formulas for the ions first. Cobalt 2, the symbol for cobalt is what? Capital C, lowercase o. Not to be confused with carbonate, which is C with a capital O, or carbon monoxide, right? The size of your letters matters. What does the Roman numeral 2 tell me? It's a positive 2 charge. So this is CO 2+. And then phosphate. PO4 3-, because you memorized it. So hopefully you made flashcards. Keep those out. Keep reviewing them, okay? CO 2+ and PO4 3-. How do I put these together so that the charges add up to 0? So if you're good with math, you might consider what's the least common multiple. So 2 and 3 are both factors of 6. So if I get a total of +6 and -6, I could get this neutral. You could do the crisscross thing. You could take this 2 and bring it down as a subscript for the phosphate, and the 3 and bring it down for the cobalt. But I'm going to show you the tedious drawing it out method. So right now I have a total of -3 and +2. And that's not going to work. I need more positive charges, so I have to draw another one of these. CO 2+. So now I'm at +4, but I made too many positives, so now I have to put in another negative. So PO4 3-. So now I've got -6. Now I've got too many negatives. This is like my Grandma Johnson bread and jam. She called it bread and with it. You take a roll and you take some jam, and then you eat the roll and there's some jam left, so then you have to take another roll, right? But then you don't have quite enough jam for that roll, so you have to take more jam. And it's always unbalanced, right? She was a rather large woman. She gave great hugs. So this is like, we're going around in a circle. Well, just keep at it. So we need another positive one here. And now we've got +6 and -6. So I need 3 of these and 2 of those. So CO3. PO4 is a polyatomic ion, and I have 2 of them. So I need to put parentheses around it and put the 2 on the outside so it isn't confusing. Any questions? Yeah. The crisscross method works too. Yep. Crisscross would take this 2 and make it the subscript on the phosphate, and it would take this 3 and make it the subscript on the cobalt. Yeah. You just always have to look and see, could that be reduced? Because occasionally, like that other example, you have to reduce it. Any other questions? Going to finish out this section. Hydrates. some ionic compounds, when they form a crystal, they incorporate a very specific number of water molecules into the crystal. And because it has water in it, it's called a hydrate. So here's an example of a hydrate. This is cobalt 2 chloride, and it's got 6 water molecules associated with every formula unit of COCl2. This is this really pretty pink color. If we heat that, we can drive the water off, and then we have the anhydrous version, or the anhydrate. An is a prefix that means without, so this is without water. We drive the water off. Now the formula is COCl2 because there's no water in it, and the color changes. So when we're naming these, we name the ionic compound, and then we specify the number of water molecules. So this one, COCl2 dot 6H2O, that dot is not a multiplication sign. It just means these guys are together. This is cobalt 2 chloride, and then we add hexa, a prefix meaning 6, hydrate, hexahydrate. Epsom salts, which you may have used, soak in a sprained ankle or something, MgSO4.7H2O. It's magnesium sulfate, heptahydrate. So here are the hydrate prefixes. You should memorize these. We'll be using those for molecular formulas also. The one kind of weird one here is hemi, which is a half. So let's practice naming these hydrates. So CaSO4.1/H2O. We have to name the ionic part first. So Ca is calcium, right? Is calcium in group 1A, 2A, 3A, zinc, or silver? Yes. It's in group 2A. It doesn't need a Roman numeral. So cover up the Ca and what's left here, SO4. What's the name of that? Sulfate. So calcium sulfate. And then the prefix for 1/2 is hemi. So hemihydrate. Anybody wondering how you can have half a water molecule? You can't have half a water molecule. By convention, we always write these with the regular ionic formula here. What this means is that for every 2 calcium sulfate units, there's 1 water molecule. So that's why it's a half. What would this one be called? CaCl2.2H2O. Well, it's calcium again, right? And it still doesn't need a Roman numeral. Calcium chloride. And then the prefix for 2 is dihydrate. The hydrate business is just a really small part of what we're doing here. Barium hydroxide octahydrate. So we need to look at the 2 ions and their charges so that we know how to put them together. So hydroxide we memorize has a -1 charge. What's the charge on barium? 2+ because it's in group 2. So you can do the crisscross or whatever method you like. It's going to be BaOH2. Octahydrate means what? 8. So I just put a dot, 8H2O. Barium hydroxide octahydrate. Any questions?